by 10 to the 22. Now we multiply this by 6.673 times 10 to the power negative 11. So we got this big huge number, right? This one, this one, this one, this one. So it's gonna equal this now. 300,285. 300,285, and then 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. Yeah, times 10 to the 6th. And that's equal to what? On the right side, you have the sum of their kinetic energies, right? So we took care of the power of the 10. So all that's left is V1 squared plus 3V2 squared. Okay, so we've got that. Now how do you solve for V1, V2? There's two unknowns. So they're crashing into each other. We said that their initial potential energy is changed to a lower potential energy when they crash. Then it's converted into kinetic, but they each have different kinetic. So now we need to use the fact that their momentum is conserved. Their initial momentum is 0. When they collide, their final momentum has to be the same in opposite directions. So M1 V1 must equal to M2 V2. In other words, what I'm saying is their magnitudes of their momentum have to be the same. One is going to be this way and one is going to be that way. So all I need to do is really to have here 2 times 10 to the 30th V1 is equal to 6 times 10 to the 30th V2. And then you cancel this, and then V1 is equal to 3V2. And all you have to do is then substitute it here and we solve it. So we got 300,285 times 10 to the 6th V1 squared, so that's going to be 9V2 squared plus 3V2 squared. So all we need to do is divide this number now by 12 and then square root it. Okay, we got it. So the velocity of V2 is going to be 158.2, and that's going to be 1, 2, 3 kilometers per second. Because it was 188 point something, so that's meter per second. So I changed it to kilometer per second. 158.2 kilometers per second. That's pretty fast. Okay, that's roughly about. If you look at our solar system, just to give you an idea, average orbital speed. So if you look at our solar system, the orbital speed of Mercury, as Mercury is going around the sun, orbital speed of Mercury is 47.9 kilometers per second. See, so this one is going to be a little bit faster than that, even about 3 times faster. So that's the velocity of the heavier star, right? Well, the velocity of the lighter star is even going to be more, which is our sun. So you're going to be that times 3. So it's going to be 474.6 kilometers per second. Okay, so now let's answer part B. If you have a comet that goes from infinity and goes through their center of mass, what is the velocity of that comet? So, well, we first have to calculate the center of mass, right? So here comes physics 1 material, okay? So imagine this is the star. I put the XY axis here. I have the heavier star. So I say X center of mass is equal to, this is, I'm putting the coordinate axis here, it's equal to 0, and then the mass of that guy, so it's going to be M2X2 over X1 plus, over M1 plus M2. So this is going to be 6 times 10 to the 30th times the X2 is the distance between them, which is, what was it, 40 times 40 times 10 to the 8th over the sum of the masses, which is going to be what? 2 plus 6, right? 2 plus 6, which is 8, times 10 to the 30th. So this is the mass of this guy, which is 6. The mass of this guy was 2. So now we get this one, it cancels this one. 6 over 8. 8 goes into 45 times. 6 times 5 times 6 is 30. 30 times 10 to the 8th meters. So that brings us about here, huh? If this one here is 40, and what was the radius of that? 9. Radius of here from here to here was 9 times 10 to the 6th. No, sorry, 9 times 10 to the 8th. And then if this one was 40, and then what do we get here? 30. So if you do 40 minus 9 is 31. 40 minus 9 is 31. So the center of mass is just a bit to the left of that. There it is. There's the center of mass. Okay, now if you allow the comet to go there, what is its velocity? Well, now what's going to happen is when the comet goes there, it's going to have potential energy with both of them. Okay? So no longer is the potential energy of both the stars relevant, the potential energy that they have with each other. What matters now is the potential energy that the comet has with respect to or with both of the individual ones. So we say the potential energy initial of the comet is equal to potential energy final plus kinetic energy final of the comet. Okay? So the initial potential energy, if the comet starts out way at infinity, it's equal to 0, it's unbounded to anything. The final potential energy is minus g mass of star 1 times mass of the comet over the distance between this and this, which we'll call x bar. That's the distance of the comet from star 1, minus the potential energy that the comet has with respect to the second star over the distance between here and here is 40 minus x, right? 40 minus x bar. And plus the kinetic energy of the comet. And the mass of the comet cancels out. And you're left with, this goes here again, so you're left with 6.673. Let me make sure I got that right. 6.673 times 10 to the minus 11. And you have the mass of star 1, 2 times 10 to the 30th, divided by the x, which is 30 times 10 to the 8th. And then this one goes over here, becomes plus. This one goes over here, also becomes plus. 6.673 times 10 to the minus 11. Then the mass of the other star was going to be what? 3 times that, right? 6 times 10 to the 30th divided by what is the distance there? Well, from here to here, from 30 to 40 is 10. 10 times 10 to the 8th. And that's equal to half b squared. So let's calculate this. Let's see what kind of an answer this gives us. So I'm going to factor up this g first. I'm just going to calculate this. 2 times 10 to the power 30 divided by 30 divided by 10 to the power 8 plus 6 times 10 to the 30 divided by 10 divided by 10 to the power 8. So that's, I added them. Now I multiply it by g. 6.673 times 10 to the power negative 11. I get 4486666 after a lot of sixes. Then I multiply that by 2. And then square